Start. Welcome everyone to our second invited talk for this conference. So I'm Ron Steinfeld, and I'm very pleased to introduce our speaker, Mehdi Tibouchi, who is going to talk to us about mathematical problems arising from timing attacks on signatures and their countermeasures. So Mehdi, let me tell you a little bit about his bio. After obtaining his PhD in computer science from University of Paris 7 and University of Luxembourg in 2011, Mehdi joined NTT Japan as a researcher in cryptography. He's now a distinguished researcher at the NTT Social Informatics Labs and a guest associate professor at Kyoto University. His research interests cover various mathematical aspects of public key cryptography and cryptanalysis, particularly related to elliptic curves and Euclidean lattices. And Mehdi has made several quite interesting contributions in these areas over the last few years, and we are looking forward to hear about them today. So welcome, Mehdi, and thank you.
So thank you very much for the introduction and for having me here. So this talk is about basically collections of good excuses to mathematics. But I guess it's one of the things that makes crypto exciting that you can meet many people here that have a large variety of backgrounds, a large variety of reasons for why they came into the field. So you see people from first computer science, more or less theoretical. You see people from electrical engineering, or math, stats, physics, social sciences, and so on. And they all have you have a lot of occasions to learn from the backgrounds. And they also come for various reasons. So people come to crypto, for example, because they are seriously concerned about the implications. Maybe, or they want to contribute to society by protecting the internet. Okay? So some people want to, attack chips with lasers, or they came because they found some topics like zero knowledge proofs really fascinating, or people come. We have a few of those coming to our research groups recently, like interest in cryptocurrencies for various reasons. So in my case, I guess I was looking for interesting mathematical problems to solve. So I did my master's in algebraic geometry, number theory, and I got a bit frustrated by the abstract sense. So I was looking for, so I guess number theorists often think of crypto as applied number theory. So of course, when you come into the field, you realize that that's not exactly true, but I had those ideas, and so that's one of the reasons that I started getting into crypto. And getting into crypto, I found a lot of interesting problems, and I realized that I mostly couldn't solve them. So fortunately, I got to solve a couple. So that's to reassure the students in the room, so you can definitely start a career based on just a few. So there is kind of a recipe to this. So this talk talks about something called timing events. They are examples of side channels. So there are ways to break ecosystems using additional information that you collect from the physical phenomena that happen while the ecosystems are running. Right? So in this case, it would be the execution time of the algorithms. So nowadays in particular, the most relevant for, say, big CPUs, would be cache time attacks. So those things basically allow you to break implementations that contain branch instruction like if then conditionals, or memory accesses that depend on some of the secrets, because they basically reveal what the secrets are. And the reason for this, I won't go into details, is because basically you can ensure that the different branches, for example, or the different places that you access in memory might end up in different cache lines in the CPU, and you can evict some of those cache lines to make sure that accessing some part of memory becomes much more expensive than the other part, and so you can decide which of those your secret corresponds to. And so it happens that, for example, attacks on TLS, for example, are much more common through side channels than through actually breaking underlying crypto. So if you care about things like secure deployment, that's really important to address. But of course, so the way I approach this in this talk is, so it's an important problem. The way I approach it in this talk is that it's a great source of tractable mathematical problem. So usually when in math, when a problem is too hard, but you look for some easy special cases, or you look for some simplifying assumptions, and that's basically the sort of things that Timing can give you from a mathematical sense. So let's say solving LW is too hard. So let's try and solve LW with some extra piece of information about the secret, and then it might become easier to do. So I'd like to give you several examples of this, including problems that are already solved by various people, including colleagues but not necessarily. And problems that are still open, I think are decent targets if you want to try. So they are not like impossible problems to solve for the most part. So mostly I will the talk will be in two parts. The first part will be about Schnorr-like signatures, like ECDSA or something. So related to discrete log. And the second part will be about lattice-based signatures. I wanted to talk about plenty of lattice-based signatures, but the talk was definitely getting too long, so I am focusing on one specific one, called Bliss, which is a bit old-fashioned, but it's a really good test bed for those ideas. Okay, so let's start with the ECDSA thing. So ECDSA, Schnorr, etc., they're probably the most popular signature schemes that rely on the hardness of the discrete problem. Most of the signatures, I mean, you might be using RSA signatures sometimes, but nowadays, I guess most people use CDSA. And so the signing operations involve some randomness that people call the nonce for the time. And so that's a bit of a misnomer in the sense that the nonce in crypto is supposed to be something that should not repeat. And indeed, if you repeat the nonce in CDSA signatures, then it's really bad. So you can immediately become a spread key. But it turns out that this nonce value in ECDSA is much more sensitive than just requiring it not to be repeated. And a little bit of leakage on it is going to be pretty bad for you. So that's the setting. So you have Alice that signs and not that receives signatures, and so in that setting, so Alice has her secret PX, denoted SK some that follows, and R is some uniform random value, and it satisfies. So it has the verification equation, which in Schnorr looks like this. So it's R equals Z plus AH HX mod Q, where so Z is part of the signature, and H is the social part of the signature. So that's depends on the variable you look at, but you can think of HZ being the signature, and H is computed from the signature, related to the message. And so that's what the signature looks like. And of course, so if you reuse the same R twice for two different signatures, then you can immediately recover the X, which is the same key. So that's pretty. So what happens if R is slightly biased? So for example, in the sense that you know the top 3 bits of the bias of the R, which is denoted K, I'm sorry, here, depends on the. So usually in ECDSA, it's denoted K, it's denoted R, sometimes in short. It turns out that so there are various techniques to attack this, and recovering X with that type of information and several signatures with the same type of linkage is mostly amounts to an instance of something called hidden number. I'm struggling with the key thing. So what sort of how do those type of leakage occur in the real world? So can be a very implementation error. The famous one is the PlayStation 3, Sony PlayStation 3, which in 2011 was openly broken by a group of hackers who noticed that basically the signing algorithm, so that the thing that checked if some software was allowed to run on the PlayStation 3 was always reusing the same nonce for signing. So it was very easy to recover the secret key based on two different instances, two different pieces of software that were legitimately signed. So that was an example of an implementation error. So it could have happened because of faulty RNGs, for example, for virtual machines. So section education is one we are interested in. Can happen with fault attacks. Okay, so for specifically from timing information, you can often recover some information. And again, it's also coming back to what I was saying later. It's a kind of good target. So so Schnorr has a proof of Schnorr signatures have a proof of security. So if you can attack the properly implemented Schnorr signature, then it means that you're able to solve the dispute problem, and that's hard. Probably too hard to give to a student as a master's thesis project. And compared to that, like say breaking Schnorr signature with repeated nonces, then it's just one division, so it's a bit too easy. So timing attacks get you kind of a nice middle ground because they're not trivial problems, but not impossible either. So they're a good way to write Google papers. So the sort of leakage that you get depends a bit on the specifics of the timing attack. For example, there's various examples of timing attack that basically give you some noisy information about the bit length of the nodes. So it tells you if roughly how many top bits of R are zero. Which is already a very interesting sort of leakage. There are weaker leakages that are present in some libraries. So for example, we have this paper about something vulnerability called data leak. Basically, gave you information just on the top bit of the nodes, And even that information was not completely perfect. So you could recover maybe 95% of the top bits, the nodes, something like that. And so these are examples of interesting leakages that you can try. So I told you about the hidden number of points. So that's kind of an abstract version of the situation. So basically you have HI, RI uniformly random elements of Z and Z. You have M of those, and they all satisfy a relation of the form. So Zi equals Ri minus Hi SK. Where I give you Hi and Zi for all of them. And I give you some information about the RIs. So in this case, for example, the N of the top bit, the N most significant bits. And your goal is to recover the secret key from that information. So that's almost the same as the leakage problem for CSA, for example. And the question is to what extent can do this? And basically, so there are two main approaches to this that I can discuss today. So one is based on lattice reduction, and the other one is based on Fourier analysis. So the one based on lattice reduction tends to require fewer signatures, but requires a bit more leakage. Whereas Fourier analysis can target very small leakages, but requires more data, so more signatures per break. And in general, so whatever the attack approach, the sort of question we have is, so what sort of non-leakage that can I attack in practice in my specific setting? So given a certain type of non-leakage, for example, if I have the top n bits of the nodes, you have a group of certain size, I'd like to define an attack that doesn't require an impossible amount of signatures. That is reasonably fast, so that doesn't take the age of the universe to complete, and that succeeds with a low probability. And so if I can have this, then I have a VLC attack on myself. And so the state of the art is roughly this. So you have on top the number of bits of leakages. So the top, thinking again about the leakage of the top bits. So for example, we know how to break 384-bit groups. If you have 4 bits of leakage, 256 groups, if we have 2 bits, and so on and so forth. And so the attacks in green refer to attacks based on Fourier analysis. And the purple one are for lattices. So you can see that Fourier analysis tends to be able to break a smaller leakage, but it tends to require a lot more signatures. So Fourier analysis first. So this attack was basically conceived by Leichenbacher. He presented it apparently at the meeting of the IEEE 1363 working group. That's the group that was working on standardizing ECDS at the time. So he was, I guess, supposed to publish a paper about this, but the paper was never published. So we only have a small amount of information on the actual attacks that remains. For example, he did a run session talk at Crypto in 2005, and the slides are still available. And the slides are exciting because I still can't, I would say, I still don't know how he was able to break some of the parameters that are written in those slides. And so that's still a mystery. If you want to replicate the results from that slide deck, that's an interesting research project, actually. And so this was revisited in a number of papers in the last 10 years. So starting from one by the random method, this 2030, and a few more after that. And so what's nice about the attack is that it can exploit, let's say, arbitrarily small bias. It can also handle noisy data out of the box. So if you have, it happens often in sessions that your data is a bit noisy. And this is not usually a problem of analysis. So what's the idea? The idea was this, if I look at the distribution of the nonce set, for example, if its L top bits are 0, then this distribution is going to have a large first Fourier coefficient. Because the distribution is a step function of Q, so it's the Fourier coefficient basically follow a sine cardinal function. So the idea is clear in this. So if you have a uniformly random nonce, then the value exponential 2i times Ri are going to be roughly uniformly distributed on the subset. But if the top bit is 0, then they are all on the upper half plane. So if I average them, then I will get something which is basically vertical. And so that's not going to be close to 0. That's going to be large. Whereas on average, everything is uniform. I'm going to be getting something small when I average. That's basically the idea of the attack. So what this means is that if I write Ri as Zi plus Hi plus K, and I get many signatures, then if I guess Sk, I can detect it by observing that it has a large Fourier coefficient, whereas all the other possibilities are all possible delays are going to give me a small value for the first Fourier coefficient. So that gives me a way to identify the key value of this, except for the fact that I need to guess the exact key. Of course, I don't want to do exhaustive search on the exact. So that was the second trick, which is that I can make I have a trick to make this peak in Fourier coefficient larger at the cost of making the peak less high. So it can become broader, but and so the way to do this is taking suitable linear combinations of samples. So basically, so if I take the sum of independent samples, so the Fourier coefficient is a convolution, so the Fourier coefficients are going to get multiplied together, basically. So the peak becomes less tall. But if in exchange for that, the Hi value becomes smaller, then so the peak broadens and values that are close to Sk but not exactly equal are also going to have a large DFT coefficient. And so if I manage to bring them in, say, an interval like 0 to L, then 0 to L minus 1, then I just have to check the Fourier coefficient of one value and one every Q over L values. And so this can be done with a single endpoint detector. And that's basically the idea. So how do I do this reduction? So the idea is, yeah, as I said, so you take linear combinations, let's say with the ternary coefficients. And in that case, I win if so the linear combinations give me the values of H that are small, so less than the range of my possible FFT, and also sparse in the sense that so their Hamming weight are not too large. And need to make sure that the Hamming weight ensures that even if I multiply those DFT values together, I'm still above the noise at the bottom, which is roughly so I'm summing, let's say M. I'm taking the average of M values of magnitude less than 1. So when I have exactly 1, so when I average them together, I expect them the average, since they are random, to be around 1 over root m. So I need to be above this noise floor for detection. So that's the second condition. And so this means that basically I'm looking for small and sparse linear combination of values, the values hi, which is related to the k-sum problem. The k-sum problem is, can I find, so I give you a long list of numbers, and you have to find sum of k of them that sum to 0. So in this case, you don't want to sum to 0, you just want to sum to something small, and you don't want a single solution, but you want many of them. But basically, the same techniques that apply to k-sum also apply to this setting. So one way to do it, for example, is I sort my list of hi, and I take the differences of successive values. And if I do that, at every step, I reduce the size of the value by roughly log n bits. I have a list of m of them. And so if I do it several times over, I'm able to reduce to whatever interval I have. It's just that at every step, I double the number of elements in my sums. So I have to make sure that I remain above the noise floor. So this is the technique that we use in a certain protein paper to break 160 bits ECDSA with 1 bit noise leakage. And it's really simple to implement, but the space complexity is large. So we need many of those many signatures, about 1 billion signatures to make this work. So that's a bit expensive in terms of space complexity. Yeah. So you can do better. Actually, so there are better algorithms than this trigger one for k-sum. So for example, there's a classical algorithm, the four-sum problem. Basically, it's a variant of the Schober-Shamir algorithm that has a better time memory trade-off. So basically, you were able to reduce as much with square root complexity, square root space complexity compared to the search and inference one. And so that's really nice. And so the property of this algorithm is that it can be beneficial for you to actually output, so at some step, output more solutions than you started from. So expand the space so that you reduce more in a subsequent step. It's a bit complicated. So you have to model, if you want to predict how this performs, you have to model in some way at each step. So what is going to be the best number to keep track of in your list, depending on what sort of memory budget you have, and what sort of amount of starting data that you have, and so on. And so this can be modeled in a very simple way. So you have an equation like this that gives you the erosive behavior of how get gram and juice for some value. That relates to the number of input samples, the number of output samples, the memory that you're locating this, and the time that you're locating this, and the number of solutions, of collisions that you want to obtain at the end. And so this is basically a linear relation in the logarithm of those values. So it means that you can model everything as including all of your constraints as just a linear program. And so you can get the best possible attack by just plugging everything in a linear program somewhere. That's a nice equation. So it has some limits. So the trade-offs are heuristic. So they don't. So the trick is that sum of uniform distribution is no longer uniform. So the precise modeling of what happens is a bit more complicated compared to, for example, XOR, where everything remains independent. So that's basically Also, another point is that this only takes into account this powdered Ramji algorithm case for sums. And there are more advanced case algorithms like something called dissection or other trade-offs more. And so you can ask if they include some particular types. So I saw a discussion in which we realized that using a certain file system algorithm could actually be beneficial in a specific attack setting. But we never got to implement. And so I also described the attack in terms of most significant bits. But it applies to, say, for example, leakage on the least significant bits or other consecutive strings of bits or something like this, with some caveats. It applies to noisy leakage, as I explained. But more generally, it's a bit tricky to characterize the biases that can be attacked in the support. And this is still not conventional. So to give you some two examples, so one is so that's a bit of code that was presented very recently in the Wolf SSL library. That's the same that's the generation of the nonce in DSS editors in that library. And so it generates some at the top you see it generates some random value. At the end it checks that the value is less than Q and it repeats if it's not. But it does something crazy in between, which is set 2 bits of the top, 2 bits of the top byte to 0. So that's the real thing. And so 2 non-consecutive bits are first 1 in the first byte. And so this is not a top it's not an MSB leakage, but it still results in a large Fourier coefficient, and that depends on specific value of Q. And we verified that, for example, for the 160-bit DSA over a prime of size 1024, it required just about 1,000 signatures to recover the same key. And so that's these people reported the vulnerability. It turned out that the vulnerability had been disclosed earlier, but and it is now fixed. But they consider this vulnerability to be they said non-critical. And so it's crazy that for me that just being able to completely recover the key from 1,000 signatures considered non-critical. And so this is a vulnerability that was present in the Wolf SSL code and its ancestors for basically as far back as we could look. So who could have the idea of setting 2 bits of the nonce to 0? I have no idea. And that's one of those places where I'm usually not a conspiracy theorist, but this one you won't know. Okay, so that's an example of a non-MSB leakage that you can attack. Here is an example of noise leakage that you can't attack with this approach. So suppose that instead I give you 1 bit of leakage on the nonce, which is the Legendre symbol. So I tell you if it's a square or not. Well, this is still 1 bit of information. I mean, information is very sense. But I can prove that this cannot be attacked with the Legendre approach, because you have a bound on exponential sums by Bombieri that tell you that in this case, all the Fourier coefficients are negligibly small. So it's impossible to attack with the Legendre approach. So we don't really have a nice characterization of the class of leakages that can be attacked. So that's an open problem. Second open problem is so this is a specific one leakage. Can you attack it in some other way? I guess we have no idea. And of course you can extend it, so it applies even if I give you more bits of leakage by telling, for example, the Legendre symbol is in the image of some specific polynomial, of any degree, any small degree, with the same reason in the path. And the last one is so the most significant 1 bit leakage give you a certain a certain magnitude for the highest first Fourier coefficient. So is this magnitude the best you can get from what we dictates in the information theoretic sense? That's a natural question that I've had for a long time. I don't have an answer for it. If you do, then I'm happy to hear it. So let me tell you a bit about the lattice approach. I won't be too long, hopefully. So again, you have the information about the secret key that you can write in this form. Basically, you have some sort of the secret key. This can be written as either from an affine combination of the affine function of the nonce Ri, which you know is kind of small. So that can be naturally interpreted in terms of lattices. So it has Ri corresponding to a short vector in a certain lattice. So I give you a description of the lattice here. It's not important, but so basically there are various ways basically to describe this lattice. So that's one specific one where the nonce is basically exposed as a short vector in the lattice. It's maybe more natural to represent it as a closed vector to a lattice of one dimension less. Doesn't matter much. But so basically, so if you believe standard heuristics on lattices, you can attack if you have if you can solve SBP in a lattice of dimension m+1, where n is larger than roughly the bit size of q divided by l, so the number of bits application, minus a small constant is related to this heuristic. Yeah, so it means you can expect to solve the HNB if you can solve SBP in a lattice of dimension slightly larger than this. So maybe, for example, L equals 2 for 256 group, 256 bit groups should be tractable. L equals 1 for 192 bit groups might be very tractable as well. But neither of those have been achieved so far in the lattice setting, whereas they be done for rational, of course, with many more signatures than just one. So yeah, so of course this is a heuristic estimate, and what doesn't feel good about this heuristic estimate is that so it's based on something called the Gaussian heuristic. It tells you that so in my static lattice, the number of lattice points involved behaves as it would in a random lattice. And this is kind of reasonable for large lattices, if M doesn't go large. But you can check that for small lattices, if n becomes large, this is no longer true. So for example, the lattice has many vectors of length q, and q becomes smaller than the shortest vector predicted by the heuristic. So it's kind of a weirdly shaped lattice from the point of view of the standard lattices. And so we have an idea of so several papers have sort of conducted experiments on those lattices, and so we have some ideas of how lattice function performs, but the precise model of the behavior, as far as I know, remains suspect. So that's an interesting point to work on. And so I really would like to estimate, so for example, the success probability of some specific variant of the lattice tax, embedding or something, on a specific small bias HDGN systems, and so that would be interesting goal. We don't have that right now. Another point is that that was made by Albrecht and Kenina recently, was that so the previous heuristic, which I told you is wrong, but let's pretend that it's not, tells you that there is a limit on the number of bits of biases that can be attacked by lattices to work. So in this case, something like 0.4, 0.25 bits would be the absolute minimum that you can reach. We don't know if this is true. But it might be, this is plausible for HND. But it turns out that Schnorr-like signatures are not exactly as HND because you have one extra amount of information compared to classical HND, which is that you have the public key. So you can check if the candidate solution is the correct solution, the correct secret. And based on that, it turns out that you can use this extra information inside lattice reduction to get beyond the theoretical mean. So in this case, they used Albers and Henniger use this inside seeding. So seeding gives you many vectors. You can ask for more vectors than you expect you need to solve the function, and inside select the correct one because you have a way to check, and you can't do this from a plain nature. And last point I want to make is so can you use more data and more time in this algorithm? So classically, it was thought that lattice attacks don't improve if you get more data or more computation. Because, so basically, if you use more data, more signatures to construct for lattice, what you get is just a larger dimensional lattice. So it's harder to reduce. And in addition, you reduce the gap between the correct solution and the normal shortest. What should be the shortest vector if it was around the lattice. So everything becomes less. But actually, so we noticed you can use more data in our computation by exhaustive search trees. For example, if you put more data, then you can throw away some of it and pick data, just keep the data with say some of the top bits of H equal to 0, and this effectively amounts to this is basically equivalent to using the module size by k bits. So it improves the attack. And similarly, you can if you have more time, you can do exhaustive search on top bits of escape, and it has a similar effect. And actually using the batches CDP techniques, but this is better than just costing you to the plain one compared to the normal one. And so these are nice improvements, but they are not nearly as large as what you get in more data or more time in relation to national time, for example. So it's kind of a double problem for us to again to ask if we can do better than this. So if there is a way to dramatically improve the attack, if you have lot more data, a lot more time for computation. Oh, yeah. And so the final question to express is so let's say you are in the attack scenario or the standard timing attack scenario for AT of Pluto for ACDSL. You have many signatures, and for each of them, you have some idea of what the number of top 0 bits of the nonce is. But this estimate is noisy. So because your measurement is not perfect, because the side chart is not perfect, and the goal is based on that information. What's the best attack that you can run? So ideally, I give you a Q, I give you a noise distribution, and you can predict how many signatures I need to make with one half of 50% probability using that sort of obligation. And we have some tricks. We have some ways to predict what happens, but we don't have an answer to this question yet. So that would be a really interesting one. And so I give you several examples of biases that you can attack with this attack. I give you some examples that cannot be attacked, but could be attacked by other techniques. But so another question is if there are sections of distribution other than the exact uniform distribution. And that's kind of a silly remark, but if your distribution is not exactly uniform, but statistically close to uniform, that's perfectly fine. And so in particular, I mean, that's kind of an obvious remark, but that's a point that I want to make very often when we see people discuss this on the internet, which is that so most of the time when you implement this CSA, you work in a group which is of a number of order very close to power. It's the power of 2 plus something which is less than the square root. In that case, it's perfectly fine to sample your randomness, your norms, as a uniform number of m bits, instead of trying to fit a uniform thing exactly in the 0 to q minus 1 interval. So the security is the same, and avoiding the rejection sampling saves you potential selection as well. That's the better way to do it. An amusing example where this statistical inequality is also relevant is something called GLBTS optimization. So there are some ellipticals where you have an additional homomorphisms, for example, a fast homomorphism that whose square is multiplication by mass. To use it for scalar multiplication, basically by R, you end up having to represent R as the number of the form R1 plus lambda R2, where lambda is the square root of minus 1. And so you can do this by first computing R uniformly, and then finding R1, R2 using some sort of statistic. Basically, that is reference dimension 2, and you can compute a short basis. You can compute a short basis, so it can be done efficiently. But often it ends up with some sort of section indicating R, so it's a bad idea in general, or very bad. So now, an alternative approach is to sample R1 and R2 uniformly into double interval, property of size square root, and not compute R2, because you just multiply by R1 and R2. And so this avoids some amount of computation, so it doesn't leak. But it leaves open the question of whether this is secure, in the sense that if you do this, then does R become unique. And the funny answer so far is that this is fine if your elliptic curve is a prime order. This is also fine if the elliptic curve has the cofactor, which is a sum of 2 squares. And the proof is a bit of familiarity with the Gaussian integrals. But for all of the cofactors, so if the cofactor is 3 or 7, then the answer is we don't know. And presumably you have, so it would be interesting to see if this is secure or not. And we can be made secure or not with suitable choice of interval. And also it should probably be easy to extend to other fast homomorphisms. But this is also an open problem. I advertise. Yeah. So that's it for EAT. Let me for 64 let me talk about this specifically this. So for this, they said is a 10-year-old computer system now, signature scheme now. So it's kind of ancient by the standards of this computer. But it's a really nice playground. So this basically speaking like people have tried section attacks for the most of the time, and it's a nice illustration of all the challenge involved, even in implementations of this systems. Yeah, so it's from 2013. It's not an easy candidate as you know this. So and presumably that's because of section X. So this uses Gaussian sampling and complicated rejection sampling as well. And this makes the scheme difficult to protect against section. So the scheme looks like this. So if you're familiar with the Kirchner style algorithm, it is familiar. So you first sample some sort of high mean randomness, in this case using a fairly large Gaussian. Then you produce a challenge value using a hash function. and you generate the signature vector Z as basically S times, so the secret key times the challenge. In this case, you plus or minus, and you add your hiding random messages. And you have this rejection function step afterwards. It works. That makes sure that the distribution of Z is independent of Z. And at the end, you return basically Z, Z2, Z1, Z2, and C, except that Z2 is compressed. So the rejection function step is a good target for such channels. So you could do it in a straightforward way, maybe, but in the implementation of this, it's done in an optimized way to make it fast. That is basically amount to iterate and randomly try this. So just calling something depending on the bits of a certain value, which is the Euclidean norm of SC. And you can read up as a result the value from the linkage. And this allows you to recover it. So the sampling algorithm. So the important part is that it depends. It does coin flips depending on the bits of the secret value k minus norm of SC. And so if the value is 1, there is computation. If not, there is not. So it's a branching on secret data, and it can be broken with a set extension. So, for example, you have here an example of an electromagnetic attack, where you see the ones and the zeros in the computation of the trace. It would work as well with cache attacks, if you're precising. And so the way you exploit this sketch is so norm of square norm of SC can be written as square norm. It's just S1 then S1C square norm plus S2C square norm, where C is the known values that varies. And so basically, each of those values give you one linear relation on the coefficient of S1 S1 bar and S2 S2 bar, which are elements of what's called the total area subfield of your starting cyclogram. And what this means is that so this field is of degree 256, and you have two elements. So you can basically recover everything if you have about 5 traces. 5 elements. And then so you have to so you get S1 S1 bar and S2 S2 bar, and you want to distribute it, which is S1 S2. And so solving this is something called the norm equation. So this was studied by Augerban and Silo, and you can do it using their algorithm. Actually, it's not okay. So that's what we did in our paper at the time. But the drawback is that this requires factoring a very large number, and the absolute norm of S1 S2. So this number of 2000 bits. So if you're lucky, this number is easily factored. But if you're not lucky, then it's hard to factor, and you're kind of in a pinch. But later on, we realized that this is not necessary because you have additional, again, this is the same trick, you have additional information compared to standard algorithm law, and we have the public key. And having the public key lets you avoid this complicated factoring stuff because you can get the additional information you need by multiplying that. So that was the red part. There is another part of the rejection something like post-solid, which is the blue part. And this one is much nicer because the red part is quadratic in the secret, the blue part is linear. So it's natural to ask if you can break the linear part. So it works very well, except that except for the fact that you don't get Z2 exactly. You only get a compressed version of it. So you get a linear system, but it's noisy. Our first impression when we saw that is that you get a linear noisy linear algebra in large dimension. So that's kind of an undevelopable problem. We can't solve this. But that's kind of a silly, that was a silly reaction. Because it's not LWE, there is no model reduction. Everything is accommodated. And LWE without model reduction is visible. So we formalized paper, and we observed that so I give you some points, but it's like LWE, but you don't have model reduction. And the answer is you can solve it efficiently. As you can volume of time, you don't have very weird conditions. And so analyzing this is a really cute exercise in concentration of measures around the measures. It's a nice area. And it's just the algorithm to solve it in the end is just linear list ones. It does not influence it. Of course, that's not something that I'm familiar with as someone with algebra background. So I'd like to talk about one countermeasure that we had against this that didn't work. Basically, we said something like, just to make this constant time, just run those algorithms into it. And it's fine except for this one, where the rejection probability at the end actually depends on the signal. And so basically, this breaks the problem as well. So then you have a different type of linkage, but it also breaks fairly easy. So, I'm skipping the slide, but it's a cute result. And so the last question is, can we have a secure implementation of this? And so for the rejection, okay. So there are several options. So as we said, so option one is to run and think the constant number of times. That's a big option. Option two is to avoid binary motions. So that's you get something like this of G. And it kind of works, but it's much less efficient than this system. And option three is to numerically compute the real. Of course, now there are new approaches. You see, if you saw the G plus G yesterday, probably you can avoid rejection something in different ways completely. But that's beside the point. But so if you want to implement this, you can numerically compute the rejection something in probability constant time. And so the way to do it is machine-friendly polynomial approximation of the function exponential and finally cosine. And we have a quick way to compute that. So the way it works is so you need so you can prove that everything goes fine if you are going to approximate the distribution using with it's called relative difference sufficiently small, relative precision sufficiently small, and in this case sufficiently small means something closer like up to 37 bits of precision. And you have to do this with the function basically exponential and higher cosine and so. And so it's doable, except for the fact so we want to do it with integer coefficients because we want to implement everything in integers in fixed points, and that becomes kind of a lattice problem, except that the CDP problem is low dimension. Except for the fact that the norm we use is the infinity norm in the space of polynomials, and that's not the Euclidean one. But we can make it work still by over-approximating this infinity norm using something called the Sobolev norm. So that's a kind of different type of mathematics, functional analysis, if you want. Sorry, functional analysis that allow us to express the normal ones are over approximate the normal one by a Euclidean norm and use standard lattice reduction. And this allows us to obtain our polynomial solution. And then making the rest of this constant time is fairly easy. So for the Gaussian sampling, I mean, for the Gaussian sampling, it's not so easy. For the multiplication, it's just use quantity time without much effort. Generating C can be a little bit tricky, but it's again, if you're careful, it's not too bad. So there's the choice of the random bit. So if you don't do the choice of the random bit in constant time, which we noticed some implementation do, then there's actually another section effect just with the knowledge of bits. So if I give perfectly fine this signature with just this random bit as extra indication, you can break everything. That's also the final result. And the rejection probability we just discussed. So how do you do Gaussian sampling in constant time? So one way to do it is using tables. But if you use table, it's a very large Gaussian standard deviation of 200. So you need a very large table if you want to do it, and that's expensive if you want to do it, right? You can do it with a much smaller table, but and using techniques of like Gaussian convolutions. So that's still okay, but it requires still a large amount of memory access and randomness per sample, so it's not ideal. So the trick that we use is actually we're using a technique that's already present on this in some way, and it's mostly known as FACT, written by Ron Steinfeld and Saxan, and that reduces the problem to computing a very concentrated distribution, but so which can be done in a very small amount of table entries, combined with rejection sampling. And it turns out that the rejection sampling is exactly the same sort of rejection sampling that we did earlier. So we can use our polynomial approximations to this is fine. This gives you a constant time implementation. So it looks tricky because still the rejection probability looks like it depends on the signature, on the secret key. But actually it doesn't. So it's a general result of Yashamura box that the number of repetitions can be simulated without secret. So the free implementation is not this. And so this is old, but with timing attacks on let's say signature are still very much relevant today. So constant time Gaussian sampling is something that people work on actively today. So this is an easy case in the sense that it's fixed standard deviation and set at 0. But we also need constant time sampling with variable standard deviation and variable center. That's trickier. We have some solutions, but not without drawbacks. It's an interesting. And if you pick an implementation of the current, let's say, signature scheme, you're probably going to find some exploitable certainly. Maybe not timings because people are careful, somewhat careful about constant time, but even that we are not sure. But certainly the runner sense almost of it. And you'll probably find new interesting math problems. And I wanted to talk to you about more examples, but over time already. So feel free to come and chat. Thank you very much.
Thank you very much, Mehdi, for the insightful talk. Are there any questions?
Question about HLP algorithm. Is there any result to combine the X approach and the Fourier negative approach?
Yeah, that's an actual question, and the answer as far as you know is no. So okay, so there's this, so there's this partial answer, which is that, so in the Fourier approach, you have to generate small linear combinations, right? And so actually, so the paper by the Mulder et al., they did with the lattice reduction. So it's not related to the HNT approach lattice reduction technique, but it's kind of a lattice reduction, using lattice reduction inside the Fourier approach. So that's an interesting one, but it doesn't work very well because the lattices don't give you usually sparse enough solutions. So yeah, so combining, making use of both attacks in a way that makes both of them better is a complicated.
How about using the Fourier analysis into the lattice reduction framework?
I don't know. Okay. We don't have an answer.
Thanks.
Is compared to the existing signature and lattice-based signature, which is easier to build a non-sparse and tolerant or friendly signature. Because I think those attacks can always be improved.
So you're asking which one is easier to protect against actually?
Yes, because from my opinion, PCC is hardly to be protected.
I would say the opposite, right? So nowadays we have a very PCC has a longer history, right? So nowadays we have a very good understanding of how to implement ECC securely. And it's also easier to add additional self-protections like blinding. So you can re-randomize your secrets when you do computation to hide potential information, which is much harder to do in lattices because if you multiply by some randomness, then things in vectors increase and they don't increase more as they should. So yeah, so I would say my guess is ECC is much easier to protect. Okay, thank you. I'm sorry about coffee break. Okay.
Thank you, Roberto. So, firstly, you talk about some leakage function, like the most significant bit, ECDSA leads to some cycles. And I was wondering, does this same type of leakage functions apply to license-based as well?
Yeah, most likely. So I mean, of course, it depends on what you mean by topic. Like, so for example, in the case of bits or something like this, the randomness would be y, the y vector. And if you get, so for example, the top bit information of the y vector might be the sign. If you learn the sign of some coefficient of y, you bring this. So similar type of leakages likely. So if you get other, like if you get the lowest order bit coefficient of y, then it's harder to say because it's less.
So I don't know too much about hidden number problem. I see them interesting. So do you currently see something about how this result of hidden number problem?
No, I don't know much about it. So the thing is, it looks a lot about yeah. So there are instances that that are clearly like so. If I don't give you enough samples, for example, then it might be information theoretically hard to solve. But as long as the problem is well defined, in the sense that you have information theoretically enough information to get the secret, estimating how hard that is. You know, like, of course, the instances, as you saw, that can be solved efficiently. Can you show that some instances are hard, or can we use the same algorithm and be correct?
Thank you.
Peter, I find that in the page 34, you said that there's a batch sleep technique. So can I ask, do you implement the batch sleep technique in the code?
I mean, so it depends. So there are advanced batch CDP technique which we definitely did not implement. But what we did implement is a very simple one, which is, so if you want to do CDP, so basically, what this means is you want to do CDP with different targets in the same lattice. And so there's a simple way, simple approach to this, which is first you do a strong run of lattice reduction on the initial lattice, and then you try to solve CDP, maybe with parallel embedding, which is also requires another round of lattice reduction, but in dimension plus starting plus one. And this one we did, and it's definitely faster. Like you don't have to do anything fancy. Just doing the lattice reduction first in the initial lattice, and then repeating, and then doing the CDP is going to make the whole computation much faster.
Thank you.
Question?
Maybe let's take the
Yeah, maybe we can take first. Yeah. So thank you very much. Let's thank Mehdi again.
Thank you very much.
We're going to present a certificate of